In this video, I want to explain the operation of the CMOS switch. Here I have a mechanical switch. So when I close the switch, I'm going to connect the voltage at point A over to the capacitor at point B. Now here I have a battery, and I drew an arrow through it to show that this is a variable voltage. And in this example, I want to vary the voltage from 0 volts to 5 volts. And I want to be able to close the switch and transfer the full battery voltage over to this capacitor. In reality, I'd probably want to put a little bit of resistance in here, perhaps around 10 ohms or so, just to limit the current when I close the switch. It's not a good idea to try to change the voltage instantaneously on a capacitor. So I need a little resistance to limit the surge current in this capacitor. So let's consider how to replace this mechanical switch with a CMOS switch. So let's consider using a N-channel MOSFET for this switch. Here I've replaced the mechanical switch with an N-channel MOSFET. Now when the gate voltage on the MOSFET is at a high voltage, in this case 5 volts, I'll form an electric field here, and I'll form a channel region that will cause conduction between point A and point B. Now when this gate is set at 0 volts, the switch will be off. I'll have no electric field, I'll have no channel in the MOSFET transistor. So in the case of a MOSFET is a rather resistive device. So I don't have to worry about a large surge current in this capacitor when I close the MOSFET switch or put the gate voltage at a high voltage. So let's see how well this MOSFET can work. For example, let's say I have 0 volts set for the battery voltage. So I have 0 volts at point A, and I want to raise the gate voltage to 5 volts and close the switch and transfer that voltage to point B. Well, in that case, I have 0 volts here, I have 5 volts at the gate, I have a very strong electric field, I form a strong channel, and I do a great job of transferring 0 volts over to the capacitor. But let's look what happens when I try to transfer a high voltage. If I set this battery at 5 volts and try to transfer 5 volts over to point B, let's look at what happens in that particular case. Let's erase this electric field. Let's remove this channel region. Now we have our gate set at 5 volts, and we have this A terminal also set at 5 volts. So we want B to charge up to 5 volts, but what's going to happen? Now we have essentially 0 voltage here, so the electric field is essentially non-existent here. But as this B terminal, if it's initially at a low voltage, we have a very strong electric field here. We form a channel and we get current conduction. But as B charges up, this electric field diminishes, and at about 4.3 volts, this electric field is going to be below the threshold voltage if we say the threshold voltage is about 0.7 volts. So once we get up to the threshold voltage at 4.3 volts, this B terminal can't get any further. So we have a problem if we just use a NMOS or an N-channel transistor as a switch. Because what happens is the voltage degrades by about the threshold voltage. So we can transfer low voltages, but if we try to transfer voltages higher than 4.3 volts, we run into a threshold problem, and this circuit doesn't transfer the full voltage. So let's see how we can fix this problem. Let's see what happens if we use a P-channel transistor instead of an N-channel transistor. Here I've replaced the N-channel transistor with a PMOS transistor. Now if I want to close the switch on a PMOS transistor, I'm going to want to connect the gate voltage to ground. If I want to open the switch, then I'll connect the gate voltage to the high supply and the transistor will be off. So let's consider the case where I want this transistor to be on or closed like a switch and the gate is at ground. And let's consider transferring a high voltage. I'll set my battery at 5 volts at point A, and I want to transfer that 5 volts over to the capacitor at node B. So let's look at what's happening in the channel region. This gate is grounded. This point A is at 5 volts. That causes a strong electric field in this direction that attracts the holes to the surface and forms a conducting channel between point A and point B. So this PMOS transistor does a good job of transferring a high voltage from point A to point B. But let's look at what happens in a different situation. Let's say we want to transfer 0 volts at point A over to point B. So instead of having 5 volts here, we have 0 volts. Let me again erase the electric field and remove the channel region. So if I have 0 volts, at this point the electric field is non-existent because the gate is at 0 volts and this P region is at 0 volts. So if this B region is at a high voltage, I'll have a strong electric field here, and I'll form a channel and I'll get some conduction. But as this B voltage decreases, as it gets to about 0.7 volts, which is approximately equal to the threshold voltage, this PMOS transistor, at that point, at 0.7 volts at point B, this electric field will diminish to the point where the channel region is non-existent. We don't have enough electric field to form the channel and conduction stops. So what happens is I'm trying to transfer 0 volts over to point B, but I can only transfer 0.7 volts. If the voltage gets lower than 0.7 volts, this PMOS transistor goes into the off condition and the conduction from point A to point B stops. So again, this voltage has been, the transfer voltage has been degraded by the threshold voltage of the PMOS transistor. So although the PMOS transistor transfers a high voltage very well, it does not transfer a low voltage very well. So what's the solution? Well, let's look at the solution. The solution is to put an NMOS transistor in parallel with a PMOS transistor. When we want the switch to be closed, we'll put the NMOS gate at 5 volts and the PMOS gate at 0 volts. And regardless of what the voltage is at the battery, if we have 0 volts at the battery, the N channel will do most of the work and transfer the voltage at point A to point B. If the battery is set at the maximum voltage at 5 volts, then the N channel doesn't conduct, but the P channel does. And in this case, the P channel does most of the work and transfers the voltage at point A to our capacitor at node B. Now, if our voltage is in between, if we're at 2.5 volts, in that situation, both transistors conduct. The NMOS does some work and the PMOS does some work. So this is the solution. For any voltage at the battery between 0 and 5 volts, we can transfer the full voltage at node A over to our capacitor at node B. So in a typical circuit, we might give this terminal a name. And if this voltage is high, our switch is closed. So let's label this node with the name close, which infers that a high voltage signal causes this NMOS transistor to close, but we also want the PMOS transistor to close. So let's add an inverter over to the gate of this PMOS transistor. So the output of the inverter will connect to the gate of the PMOS. So if our closed signal is at 5 volts, this inverter will invert that 5 volts and put 0 volts at the gate. So when the closed voltage is high, both transistors are on and the voltage is transferred from point A to point B. Our switch is closed. Now in the situation where the closed voltage is at 0 volts, the N channel transistor is off, and our inverter inverts the 0 volts at the input to 5 volts at the output, and at 5 volts the PMOS transistor is also off. So when closed signal is at a low voltage, the switch is open, and when the closed voltage is at a high voltage, the switch is closed. So let me mention that a common symbol for these two transistors is this, with a bubble here, a signal here, a signal here. This is our point A, this is our point B. This is the gate of the NMOS, so it's the gate of the N channel, and this is the gate of the P channel. So when this gate is high, this gate of the P channel is low, and we have conduction from point A to point B. So this is just a simple way of drawing these two transistors. And so hopefully this gives you some idea of how the CMOS switch works. Now this switch is also called a pass gate, is sometimes called a transfer gate, and sometimes called a transmission gate.